This is, as Lukash mentioned, it's a combination of work related to reinforcement learning, mean field games, and algorithmic trading. And I'm going to present it in sort of in a developmental way without trying to burden you with all mathematical details. I'm going to hide most of them, although there will be some in there for the mathematicians in the audience to get excited. This is work that I've done through the years together with one of my longtime collaborators, Alvaro Carteo, who's sitting back here. We've written a book on the subject related to algorithmic trading, and I'll tell you a little bit more about that later, as well as with one of my former PhD students, Philip Casgrain, two of my current students, Brian Ning, Franco Lin, and on one of the topics as well, a third student, Tadao Ferreira, and a colleague at UToronto, David Duvenot. And thanks for the plug, by the way, Lukash, about the SIAM conference happening in June. I was going to do it myself, but you already did. But those who came in late probably didn't hear about it. In beginning of June, 4th to 7th, there's a very big meeting in financial mathematics that's happening in Toronto. And there is indeed a large section of talks that are focused in machine learning and a data-driven type of quantitative finance. So I certainly encourage you, if you have not yet registered or know about it, to take a look at the webpage or just Google this and find the webpage, and we'd be happy to see you there. Okay, so without further ado, let's start with the talk itself. So first, I'm going to provide a little bit of an overview of the problems that we're going to solve and the general framework that we're going to be developing. So algorithmic and high-frequency trading, and in particular, I'm going to focus more on what I'd call algo trading rather than high-frequency. But nonetheless, they are three main types of problems that people address when you think about high-frequency and algorithmic trading. First is optimal execution problems, where you take an agent has a large number of shares, an institutional investor, for example, and they want to sell it. And they're trying to balance selling that really fast, in which case they'll get a very bad price, with selling it very slowly, in which case they're unsure what price they will receive. So if you do it very fast, you're pretty sure what price you will get, but you'll have a very large price impact. If you do it very slowly, you'll have little price impact, but then there's all this uncertainty in what the future prices will be. And balancing those two things is a delicate problem. Statistical arbitrage, that's another class of algorithmic trading problems, where you try to benefit from certain sort of what you think of as statistical features or mean reverting or momentum-like strategies. So classic example is pairs trading. If you see two stocks that generally co-move with respect to one another and then temporarily they're moving a little bit apart, you might expect that they're going to mean revert and come back. And that would be a classical statistical arbitrage strategy at a very, very high bird's eye perspective. And then the third is market making, where you're both posting to buy and sell an asset, and you're willing to buy it obviously at a lower price than what you're willing to sell at, and you make money by getting that spread. Algo trading encompasses all of these, and we've worked on many various problems related to them. I'm going to focus in this talk mostly on the first two problems in a combined way, both from a mathematical modeling perspective as well as from a data-driven perspective. That's where the reinforcement learning comes in, and mathematical is where the mean field games and stochastic control comes in. So we're going to talk about both of those pictures here. And by the way, stop me at any point, raise your hand if there's any questions and so on. I don't mind slowing down for that. So to begin, here's a little bit about data and some fairly stylistic features that you see in the market. So if you look at this diagram on the left, what you see is a scatter plot of what's called net order flow on the horizontal axis. So this is the total number of buy liquidity taking orders and sell liquidity, and the difference, between buy liquidity taking orders and sell liquidity taking orders within a 5-minute time window, observed every day of the year for every 5 minutes of the day. And on the vertical axis, you have the price change over that same time window. So that means I take a time window bucket, I look at what's the difference between the number of buys and sells that came in, and what's the price change that came in. Make a scatter plot. And what you see is something that makes sense and sort of obvious, that when you have a lot of excess buy orders, prices tend to move up. When there are a lot of excess sell orders, prices tend to move down. Now, if you sort of reverse these axes and say conditioned on those 5-minute windows where the price change was, say, exactly minus 5 cents. So let's take a look at on the second plot now, the minus 5 cent point, and you take those specific bins and you look at the mean of this order flow, this net order flow. What is it? It's something that's negative, and there's a confidence bar around there because there's uncertainty in it. And if you look at plus 0.5 cents, then the mean is something positive again. It's illustrating the same fact, but reversing it and looking at it from a conditional expectation point of view. Okay. What this illustrates is that when price changes are relatively normal, relatively smallish, the impact is essentially linear from the net order flow of all trades. When you go out and you have larger transactions, you have larger price changes, then there may be some nonlinearities that feed into here. And that happens both on the negative side as well as on the positive side. I'm going to focus in and develop a model that's going to be relevant for when price changes are relatively small. And you can think of this happening on shorter and shorter time scales, so in which case the price change really is small. So that's one empirical fact. Next empirical fact is if you take a snapshot at a point in time and look at what's called the limit order book. So this is the collection of buy and sell orders that are resting in the order book that have not been executed as yet. What you see is a picture like this on the top left, yes. On the vertical axis are the set of prices that are available. The color red indicates people that are willing to buy, the prices that they're willing to buy at. The blue bars are the prices that they're willing to sell at. And the horizontal axis tells me the volume available. So this is a typical limit order book. This in particular is for, I believe, Intel at some date in 2014. And then you can ask the question, what if at that instant in time you wanted to sell a certain number of orders right away? What's going to happen if I say I want to sell 30,000 shares? I'm going to have to walk the limit order book. That means I'm going to keep walking through all of the red bars until the integral is 30,000 shares. And whatever price I receive from that, if I compute an average price per share, that would give me a sense of the price impact that that trade would have. And then I can repeat that experiment. What if I threw 40,000 shares? What if I threw 50,000 shares, et cetera? Then if you make a plot of that price impact as a function of the volume that you would send at that instant of time, you get one of the thin lines that's shown in the top right panel there. One of those thin lines. Yeah. And if you repeat that for every second over a 1 minute time period, you get 60 thin lines. And if you look at it, the approximate average behavior, it looks, again, approximately linear in the volume of your trades. Now, it's clearly not. There's some concavity in there. There's all sorts of weird, funny little kinks that happen every time that you go from one level to the next. But given the amount of fluctuation that's in the book, if you try to model this more accurately, you would get bogged down by not being able to do something that's analytically tractable, which is what we're first interested in doing. And then secondly, the amount of variability in there would you would probably not gain as much as you think you would by having a better model because of the amount of variability. And there's a question.
Yeah, sorry, are you assuming you're at front of the order book there?
No, I'm a liquid. So the order book is the liquidity providing orders that are sitting there, right? Those are still the limit order books that have not been executed, or the limit orders that are not executed. I'm playing the game, what if I was taking liquidity at different volumes? And so I'm not going to get the best price. I'm potentially going to have to walk the limit order book. So if I submitted a sell, if I was submitting a sell market order right now for 10,000 shares, well, the first level of the book I would get, or I should say maybe about the first 5,000 of those might get executed at the best price, but then the next 5,000 will get executed at the next best price.
I'm thinking about the people who put the orders before you.
Yeah, so
they would want, they surely would be first in, first out, right?
So they are in the limit order book.
I see, okay.
I'm asking the question from the liquidity taking perspective here. Yeah. I'm not modeling the order book. Okay. I'm saying, imagine this order book is here, and sure, there are people that are at different places in the queue, and it is a FIFO, right? First in is first out. Those who placed an order at that price with a particular volume will be served first or executed first if they were the first one in that queue, and so on. But I'm not looking at it from that perspective at this point. I'm looking at it from the perspective of a liquidity taker. So like a large institutional investor that's sending shares and only taking liquidity. We do have a lot of work on the liquidity providing side of things as well, but I'm not going to be discussing that today. Okay. Anything else?
Do you assume that the bids don't disappear once you start hitting them?
So this is a thought. So the question is, do I assume if the bids don't disappear once you start hitting them? So this is a thought experiment which says, here's the status of the limit order book. What would the price impact be if I had submitted an immediate order for 10,000 shares, 20,000 shares, 30,000 shares, 40,000 shares, right now for immediate execution? It's not as if I'm sending, I want to execute 30,000 shares and I send 1,000, wait a little bit, send another 1,000, wait a little bit, send another 1,000, wait a little bit. I'm just walking the limit order book to see what that immediate impact would have been. Okay? So no one would ever do this in practice, right? You would never just send 30,000 shares and walk all, 3 layers of the limit order book. But if you did, this is what the price impact would be. And the reason people don't do it is because there is this price impact. But because we want to develop a theory as to what you should do, we need to account for what would happen if you did do something that was naive, right? And then run the mathematical analysis and see what the consequences are. Okay. So once again, the idea is that this linear impact is saying that if I send a liquidity taking order right now, it's approximately linear in the volume that I will send, the impact that I will have, the price, the worse than the best price that I will receive. The slope of that dotted line there is a proxy for liquidity in the market. So if the slope is very high, or I should say inverse liquidity, if the slope is very high, that means small volumes have large impact, which means that there isn't much liquidity in the market. If the slope is low, then small volumes have very little impact, which means that there is a lot of liquidity in the market. The slope of that line, if you plot it through the day, you get what's on the bottom panel. And it has a very particular characteristic. You can see that it starts off high, fluctuates because, of course, it keeps changing throughout the day. There's a lot of fluctuation in the slope of that line. And then it settles, and then it drops again towards the end of the day. That's fairly typical. This is what you see, and the rationale for this, and this happens across a large number of assets. The rationale for this is that there isn't much liquidity in the morning. People are not willing yet to put as many limit orders into the order book because they don't know what prices are. Once that information has been impounded into the market, people are more happy, and then that stabilizes. And then towards the end of the day, there are a lot of algo traders that are unwinding their position and getting out of it. So there's additional liquidity there because they would try to unwind with limit orders first. And that makes this price impact go lower, or in other words, increase the liquidity. So those are just some interesting market features. So the two main things that I want you to take from this is this linear impact here and this linear impact here. And we're going to write down a simple model for that, and I'll tell you some stories that correspond to what happens when that is the feature that you see in the market. So this is based on some work that Alvaro and I have done on what we call incorporating order flow into execution problems and general trading problems as a whole. So this linear impact that we saw here, which is the price that you would receive if you sent an order right now, is what I would call the temporary price impact. And what this tells me is that if I send an order at a particular rate nu is how fast I send the orders, say per second, then I don't receive the mid-price S. Instead, I receive the mid-price S, or I should say I don't pay the mid-price S. I pay the mid-price S plus A times nu. If nu is positive, I pay more than the mid. If nu is negative, I sell and I get less than the mid. It's mimicking the approximate behavior that's in this limit order book. Now, we also saw that there is an influence on price changes and order flow. So so what I have there is M is a martingale component, and the first term shows the excess order flow, the net. My trading, nu, plus mu plus minus mu minus. So mu plus and mu minus is everyone else's trades. I don't know what they're doing, and I don't know why they're doing what they're doing, but I'm going to incorporate it there to account for the fact that we see that there is a positive influence between price changes and order flow. Now, you could also add some arbitrary other stochastic drift to this, if you like, and I'll talk about that in a second. But that's the base model. So you have a martingale component. You don't know where prices are going to go, but you do know that if there's excess order flow in one direction or the other, prices will drift in that direction. And your goal is somehow to optimize some problem by choosing nu. Your cash from trading is given by the equation at the bottom. So the first term that you see there, the S plus A nu, that corresponds to your execution price. It's the same temporary impact you have above. And nu du represents the amount of shares that you receive when you send an order at a particular rate nu. So the negative of that is your cash. That's how much you pay. The agent is aiming to solve this control problem. So they want to solve an optimization problem where they maximize the expected terminal value of all their wealth. So X represents the cash that you get from trading throughout the day. Q times S, the second term there in the first curly brace, represents the amount of the value of any shares that you have left over. Alpha Q squared represents a penalty that you have on having inventory at the end of the day or at the end of your trading horizon. If you make alpha very large, it will force a trader to get rid of everything by the end of the day. And the other term is a term that you can think of as somewhat like a risk term. It's related to variance. It's not. It's more directly related to something called quadratic variation. And the quadratic variation measures the amount of risk that is in the book value of your shares that you hold throughout the day. There's another very interesting interpretation of that. The first two terms are very easy to understand. The last one is the one that's a bit funky and looks a little bit odd. But you can also interpret it from the model uncertainty perspective. As I mentioned, you can imagine taking this model and adding to the drift some other stochastic process which pushes prices in one way or another due to latent factors that are in the market or other things that you cannot see. And you might want to say, how would you protect yourself from not knowing what that component actually is? That's a notion of model uncertainty. And one of the pieces of work that we did was demonstrate that if you solve that problem with model uncertainty, it's equivalent to solving this. I'll come back to that part later. Okay, so the last bit of math for the first part of the talk, and then we're going to go over into more reinforcement learning, more data-driven things, is to show you what's the optimal control that comes out of this. If you solve this single agent problem, so that's one single agent optimizing against the sea of other traders who are not necessarily optimizing, you don't know what mu plus and mu minus are, what is the optimal thing to do? It looks like this. Now, I'm going to interpret this for you. The first term that you see there, which is a deterministic function of time times q, this corresponds to the classical Armgren-Chris solution. I don't know if, hope maybe some of you are familiar with that. This is the question of if I have a number of shares and I try to liquidate it, you follow the deterministic path when your stochastic process is a martingale. It turns out in particular when it's a Brownian motion. You just follow the deterministic path and liquidate whatever you have using a deterministic function through time, regardless of what's going on in the market. Now that's obviously not what happens, and part of why people don't do this is because order flow affects where prices go. And what this formula tells you is that you correct for the effect of order flow by using the expected average future order flow given the information that you have right now. So if you look at that second term, it's an integral of some function of time times the expected future net order flow. And it has some weighting factor. So if you have no permanent impact, if b is 0, then that term's gone, which reduces you back to the martingale component. But we know that there is, in fact, impact from order flow. So this tells you how to solve this control problem, how to optimally trade in the presence of an arbitrary model for order flow. So you could put in whatever model you would like from you. I can take a machine learning model that says, okay, let me model order flow by just looking at what happened in the limit order book in the last X number of seconds, and then that tells me what the next order flow would be over the following second. Plug that in to this formula, and this will give you the optimal thing to do. Or if you take a more continuous time stochastic calculus approach, you can write down an SDE for what you believe mu has to be, plug that in, compute this expectation, and again, you have the exact formula for how you should trade. So in some sense, this is a model agnostic result that's very, very general. The key assumption that allows us to get to this result is the fact that we have these linear price impacts, which is borne out to some extent by the data. But that's where we know, but although it's borne out by the data, we do see deviations from it here and here. So that's where the reinforcement learning starts to come in now. So it says this is a fairly model agnostic approach where there's some basic set of assumptions, but the underlying model for how order flow affects things or how the stochastic drift affects things is very general. How do we get away from this particular, this limitation, the limitation of linear price impacts? That's one question we would like to ask. As well, how do we get away from actually specifying a model entirely? Because here I still, even if we believe linear impact, I still need to have a model for order flow in order for me to decide on how I should optimally trade.
What's alpha?
Sorry, alpha is a terminal penalty. So it's what forces your inventory to 0 at the end. The optimal solution when alpha is not infinite is very similar. The deterministic function of times are just different, but it has the exact same structure. Okay, so to answer that question, how do we get away from specifying a specific model? That's where reinforcement learning comes in. Now, maybe I should get a sense of who's in the audience. How are people familiar with reinforcement learning? Who is? Okay, 1, 2/3. Okay, so maybe I can go fast over this part. So the idea behind reinforcement learning is fairly simple. Or I should say, the big conceptual idea is fairly simple. The actual proof of that some of these things are valid is not. So reinforcement learning, the idea behind it is simply trying to understand how to act optimally in an environment where your actions affect that environment, that the particular state of the environment affects the rewards that you receive, and you don't want to make any specific underlying assumptions about what that environment is doing. You want to somehow learn, in quotes, from the responses of the environment, from where the environment evolves, from what state to what state, and how it reacts to your actions and what rewards it gives you. Those are the only inputs, and then you try to do some optimization problem. So it's very, very similar in a sense to this performance criterion. I'm trying to maximize an expected value of some set of reward. It's just stated in a slightly different way. And the goal is to try to do this in a model agnostic way without making a specification. So just so that notation is, everyone has the same notation here, we're going to try to maximize this performance criterion where you take the expected sum of all future rewards discounted, so gamma is like a discount factor, where you start in a particular state S at time t, you take an action A, and you evolve to S at time t plus 1 under that action A. And this mapping from S at t plus 1, or sorry, st to st plus 1 is some arbitrary mapping. You don't know what exactly it is. It could be stochastic, it could be deterministic. And the reward that you receive by taking that action is also something that you don't really know what it is. So you just want to specify to some arbitrary function of the three things. It depends on what action you took, what state you were in, and what state you get to. The states could be high dimensional or low dimensional. Doesn't matter. That's our goal. So this is a graphical diagram, a graphical model representation of what's going on. So you can think of x above as the evolution of the real world. That's all information that the world actually has. It's encoded in this variable x. It evolves along in some Markov way. And if it's not Markov, add as many state variables as you like to make it Markov. You take actions based only on S. So S are the states of the world that you take actions on. And when you, in fact, wanted to do, whoops. So you take actions only based on S. And given that you take that action, it affects the environment. It gives you a reward. Your action also determines what that reward is. From the environment, you see Y. And although you can see all of Y, you maybe make your decisions only on a subset of that. And then this evolves forward. So that's a graphical model representation of what's going on in the background here. And we like to try to maximize and solve the performance, solve for the best performance criterion over the set of actions that you're allowed. So reinforcement learning does this by going between exploration and exploitation. So the idea is to try to take a random action to explore what's going on in the environment, and then eventually roll it over into taking taking the exploitation action, which is taking the action that you know what's best right now. The way it does it, excuse me, my throat's getting a bit dry. The way it does this is by using the Bellman principle. So if you take a look at that performance criterion, you can write down a Bellman principle that it satisfies. And it can be written in terms of the instantaneous reward over one step plus a discounted future performance criteria, future value function evaluated at the future state that you happen to move into. Now, if the transition probabilities are known, you can solve this as a fixed point equation. It's basically a fixed point equation for the value function. And you can simply iterate and get it. The point is we don't want to make an assumption on that transition probability. That's where Q-learning comes in. So Q-learning does the following. It says, let's take a look at this Bellman equation. If I remove this max term and I just look at what's under the expectation, let me call that a new object. I'm going to call that the state action value function. So that's this object here, Q. If you look at the state action value function, you can rewrite the Bellman equation in terms of it. In other words, you can rewrite a Bellman-like equation for the state action value function. And again, this is a fixed point equation for this function Q. If I know Q, I know what the optimal actions are, and I know the value function. If I only know the value function, I don't necessarily know what the optimal actions are. Okay? That's the reason why you introduce the state action value function. Now, the goal is to try to estimate this function and the optimal actions just from data. So the idea is you observe S, you take an action, A, you observe the reward you got, and you see where you move to, what's the new state of the world, S prime. You update this Q function according to the equation that I wrote there. Now, this looks like a little bit of a mystery, but the reason it has this form is because if you did the following simple experiment, suppose I had a random variable, and let's call it x, and I gave you samples of that random variable, x1, x2, x3, all the way up to xn, and I asked you to estimate the mean, which is the expected value of x. Well, how would you do it? The answer is pretty simple. It's just the sample average, right? It's 1 over n, sum of the xi's. What if I asked you, now I give you one more sample, how do you get the new estimate? Well, again, I could compute the new sample mean and take 1 over n plus 1. But you could also take the old sample estimate you had and correct it. And that correction looks exactly like this. So the expected value of x can also be rewritten in terms of the estimate of the expected value of x from n observations plus the nth observation, or the n plus 1th observation, well, plus a correction term due to it. That's exactly what you have here. The Q function is satisfying an equation that is something like Q equals the expected value of a random variable x. That random variable x, if I see a new observation, now corrects my estimate of the expectation. That's the essence of this Q-learning methodology. Now you have to prove that that's truly a fixed point, and there's lots of nice theory that shows that that is under certain assumptions. Okay, so learning comes in, so when you're doing this in practice, you want to know, how do I take these actions in order for me to keep updating the Q function? And the way you do it is, as I said, exploration, exploitation. You select a random action, A, with some certain probability, and otherwise you select the optimal action based on what you know so far and what your best estimate of Q is at that time. So that's the essence of Q learning. And it doesn't work terribly well, generally, except for very small state spaces and small number of action choices. One way to improve it a little bit is to use DynaQ learning. So that's the idea of combining a model of what's happening in the data together with this Q learning methodology. So you update the Q function from real experience by interacting with the real world. You learn a model simultaneously. You then simulate from that model, and you keep updating the Q function from the simulated model. Now go back to the real world, get a new sample from the real world, update your model, simulate more, update Q functions while you're simulating, go back to the real world, and you iterate in this manner. Tends to work a little bit better. Still has limitations. In the interest of time, I'm not going to go through these two specific examples. Instead, I want to go on to another approach rather than using DynaQ to do something else which works much better when the state space is continuous and you have multiple or potentially continuous actions. And that's using the idea of function approximations by approximating the Q function by a deep neural net. Okay. So this notion is, the idea is actually fairly simple. It says, well, let me go back here. I want to find the function Q that satisfies this fixed point equation, right? The second equation that you see there. I want to find it. I don't know what it is. So why don't I just pretend or assume and approximate it as an output of a neural net? Q is, so I take in actions A and state S, feed it into a neural net. The output is Q. and I want to find the parameters of that neural net that allow that function q to satisfy this fixed point equation. That's the goal. That's the idea. And just as a pretty, maybe I don't need to do this at ATI, but let me just quickly see. Does everyone know about neural nets? Yes, yes, yes. Okay, so I'm going to flash these slides in front of you. So neural net, what is it really? It's very simple. It's just a nonlinear mapping from inputs to outputs, done in a very particular way, done by using composite functions. And those set of composite functions require you to propagate from one layer of the network to the next, activate at the particular layer, and then propagate and activate until you finally output something. And there are various choices of activation functions. Typically, propagation is affine, and the output function is typically linear, but you can choose other things as well. And how do you learn? What does learning mean in this context? Learning means finding the network parameters, which means exactly what are the parameters in the propagation function, in particular, that go into the network to minimize some loss. And the loss would depend on what the underlying problem is that you're solving. And to minimize that loss, one of the classic ways of doing this is using gradient descent, which is inefficient. So you change it to stochastic gradient descent, where you use a reduced data set in order to compute your gradients. And then there are all sorts of other fancier and more efficient, potentially, searching algorithms for finding the minima. Okay, so back to the problem at hand. How do we adapt that in this context of a Q function? Because this is not simply, if I go back here, oh, sorry, I'm going forward. If I go back here, the Q function is not, it's not that I have a loss function that depends on just data and my network. My loss function is how the error between my current Q function and what the expected one step ahead plus reward Q function is. So it's a fixed point equation on top of a loss minimization. And that's what makes this a little bit different. So the way that is solved is by saying, okay, there's the Bellman equation. I wrote it up at the top for the Q function. And what we're going to do is theta will encode the network parameters, as I said before. And what loss function do we use? We use the loss function that is essentially the difference between the left and right-hand side of that Bellman equation where the expectation is removed. So you can almost think of it as saying, we're going to minimize the loss of the Q function where I use a one sample Monte Carlo. But we're going to do this over many samples. And that's where it eventually is hoped to converge. In fact, I don't believe that there is a proof yet that this truly converges to the fixed point of the Bellman equation. It's a methodology that makes sense in some way, but there's no proper proof of it. Yes?
How do you find that max inside? Isn't that a separate problem?
To maximize Q over X prime in U. So that's, yeah, but it's a fairly easy one in a way. It's a greedy search that you can do, right? You just have all your possible states. You just search. You might want to put them in a grid and then try to find the ones. If the actions are just finite, then it's trivial, right? If it's just finite dimensional. If it's continuous, then you have to do some, some greedy search effectively. Yeah, yeah. But usually people grid it. Yeah. So the question particularly was pertaining to this maximization that occurs here. Even if I have a network that approximates Q, I have potentially a continuous value of the set of actions at every arbitrary point in state space, which is what you have just sampled. So the question is, how do you maximize over this? And that, as I said, you can just do it via greedy search, that's what's often done. You could potentially do something better. Yeah. Okay, so the update, so in this context, in the original context, the update to the Q function was done via this recurrence relation, which is related to updating the approximation of the expected value of a random variable from n samples to when you have the n plus 1 sample. Here, the update is by trying to find the network parameters now that make my Q function as close to the one step ahead value function, that a reward plus one step ahead value function. That's the DQN idea. Okay. And you iterate this process. Now there are some problems with it. So then there's other layers of complexities that layer on top. So one thing is you should use a replay memory, much like in DynaQ where you keep a model in the background. The model in DynaQ is usually very simple, just a history of what's happened in the past, from what state you went, what state you were in, what action you took, what state you got to, and what reward you got. Imagine you kept that four tuple, that history of them. You can use that as a replay buffer. And you sample from that replay buffer at each iteration in order to minimize a loss. And what you do during that sampling is, you have the sum now of all of the individual losses, but you fix one network that sits here. You fix this target network and only update it after a certain number of iterations. And in the interim time, you're updating and maximizing the network parameters that go into your model. So theta m is your model network. Theta t is a target network that's frozen and updated only after, say, every 10 iterations, 100 iterations, et cetera. And then you make your theta, your model network, equal your target network and repeat. Yes?
So rather than having the argument, shouldn't it be a learning, like a learning rate because of the potential stochasticity of the reward function?
Well, the learning rate is coming in when you do this. Yes, so when I say argmin, it's really, you use a stochastic gradient descent to minimize that loss function, and you'll stop after a certain number of iterations. Yes. So it's not, you would like to have the argmin, right? That's what you would like, but you cannot have that. Yeah, so you implement finding the argmin by doing stochastic gradient descent. Yes. Okay. Yeah, like I said, please stop me at any moment, right? Because it's unclear to me what level of understanding people are at.
Yeah, I mean, if people could raise their hands, that would be helpful because I could pass
Then you
the
can
mic.
pass the
Yeah.
mic. Yes.
Thanks.
Okay. so this is one of the little tricks, if you will, to stabilize the fixed point iteration procedure when you're doing DQN. Another issue is the fact that, in fact, let's just go here. Another issue is the fact that when you find this maximization over the actions of the one step ahead, at the one step ahead state, using the target network, you're doing this using the target network, but then you're trying to match your model to this one step ahead error. And there's some sort of inconsistency and instability that rises in there as well. So another way to do it is to replace that optimal action by the optimal action that comes from the model network. And that's what feeds in to then match your Q function on your target network, which then feeds in to give you your one step ahead reward target. This is what's called double deep QN. So there are all these little tricks of the trade that come in that you only realize works well once you start doing things, right? You start off with an idea and then certain things fail and you try to correct it. And these introduce much more stability into the analysis, into the system. So this is a little bit of an algorithm. Let me just show you some results. That's just showing you how the loss function degrades for a certain set of assets. What I'm showing you here is a heat map of an optimal trading strategy that's for executing a certain number of shares over a given time horizon. And in this case, it was very simple, just 5 steps. I think each step is 1 minute. And we're not telling you what to do within the minute. We're telling you what to do over that minute. And each one of these panels represents a panel in 4 dimensions, really. So there's quadratic variation. If I take a particular panel, say the bottom left, this is the quadratic variation of the asset price being in the low third that we've observed in the data. And the price is negative. Price relative to the start is sufficiently negative. Then, if you go through each one of those, to that bottom left panel, as you move across horizontally, you have time. As you move vertically, as you go down, you have inventory. So what this tells you, if you look at the colors, as you have higher inventory, you trade faster. Makes sense. Also, as you approach the end of your time horizon, you tend to trade faster as well. If you compare, say, the bottom left quadrant or bottom left panel to the top right panel, you see the top right is sort of hotter. It's has lighter colors. What this is telling us is, well, when quadratic variation is high, when there's more volatility, and prices are high relative to where they were when you started, you should also trade faster. So it makes some intuitive sense, the net results. And this is simply an illustration of the trying to illustrate some of the features that come out of the fixed point algorithm. Here's the results on a limited data set using a whole bunch more features as an input into the state of the system. So you have, I think, something like 16 different features, such as the volume of new buy orders that just arrived in the last minute, the rate at things were canceled. In the limit order book, remember, it's fluctuating all over the place. If the rate of cancellations is very high, you might behave differently than if the rate of cancellations is slow. You also have the volume of hidden order executions. All of those go into this. And when you do learn on a set of assets here, this is just a fairly small sample. We're doing a much more extended data set right now. You find that on average, you beat a classic benchmark, which is called TWAP, and you beat it by quite a bit. In fact, the probability of you being less than the benchmark strategy is usually more than, or smaller than 30%. Okay. It looks like around the maximal there will be actually 39% is the highest one that we have there. So this is showing you that this algorithm is really doing something and adding extra value on top. I'm going to compare some of this with the reinforced Deep Kalman filter coming up, and you'll see how that beats this as well in certain contexts. Okay, so I'm going to switch gears now. Yes?
Is that a 2014?
This is 2018 data set.
28. Okay.
Yes. I believe it's the month, training was maybe, if I'm not mistaken, September, October, November, and then testing was in December, something like this. Yeah. Okay, reinforced Deep Kalman filter. So this is a related but different way of approaching reinforcement learning. So in order to understand this model and this setup, I need to remind those of some of you about what Kalman filters are. So Kalman filtering works as follows. There's an underlying hidden state of the world. Let's call that Z. Z1 goes to Z2, goes to Z3. You do not observe this. You do observe X's. X's are your states in the world, and they could represent whatever you want. Z's evolve according to an autoregressive order 1 process. So Z at t plus 1 is a constant plus a matrix B times Z at t plus noise. Okay, so autoregressive of order 1. X's conditional on Z, t, is just an affine transformation of ZT plus noise. So X is some constant C plus D times Z plus extra noise. You only observe X's, and the question is, can you infer what are the Z's, and can you find the model parameters simultaneously? So in order to do this, in order to estimate the parameters, you need to filter the Z from observed data and so on. Because everything is Gaussian and linear, you can do this in a very efficient way. This is called the Kalman filtering problem and Kalman smoothering. Deep Kalman filters, which was introduced a few years ago, takes that essential idea and realizes that the key ingredient is the conditional normality of things. So the idea between this slide and this slide, the only difference is, well, actually, let me go to this slide for a second. The other way to state this, rather than stating that ZT plus 1 is an AR1 process, I can state it as ZT plus 1 conditional on ZT is normally distributed with a mean that's an affine transformation of Z. And I can say similarly, XT conditional on ZT is also normally distributed with a mean that's an affine transformation of Z. That's the actual essential ingredient in this model. It's not the recurrence relationship. It's that conditional normality. So the idea is use the same idea that ZT plus 1 conditional on ZT is normal, but make the mean and its variance be dependent on ZT in a nonlinear way. And that nonlinear way is through a neural net. Okay? Because it has to be a deep neural net, right? What else? So, so mu theta and sigma theta are neural nets. Similarly for X. Okay? The mean and the variance are neural nets. And this now suffers from one problem. This Kalman, in the original formulation, when you have a linear AR1 processes and conditional Gaussian, then when you do the inference, when you try to infer z, find the posterior of z given x's, it's tractable. It's analytically tractable. Here, it is not because of the nonlinearity. You cannot do it. So instead, you use variational inference and variational approximations. So the key idea is that when you want to try to maximize the set of parameters that show up in your model, or find out what are the parameters in your model, what you're effectively doing is solving for a maximum likelihood estimator. So if you write down the likelihood function associated with this generative model, you can, in quite generality actually, just by using Jensen's inequality, bound it below by what's called the evidence lower bound. So the lower bound of the log likelihood is given by this expected log of the probability of your data given the hidden states minus the Kullback-Leibler divergence. So this is between the true posterior and any other posterior that you wish to choose. So Q is any arbitrary model that you want. The idea is, again, that you would like to maximize likelihood. That's what you want to do. You want to find what's theta to maximize likelihood. You don't know how to do that. Instead, let's introduce an arbitrary model. I'm going to call that Q. And if I maximize over this arbitrary model and my data, theta and phi in other words, if I maximize this lower bound, then at least I know that all I know is that I've maximized a lower bound. And that's as good as I can do. And I can choose that arbitrary model in such a way that it is tractable. The true posterior is intractable. So one example of a variational approximation to the posterior is what I show at the bottom. So just assume arbitrarily that the distribution of zt plus 1, conditional on all the information that you have at that time, under this variational approximation is itself again normal, but now it's no longer just dependent on z at time t. It may depend on the whole history of x's as well. And you could, in principle, put the whole history of z's there. Okay. This is an approximation that you wish to that you choose. And it turns out that under these kinds of assumptions, you can write down analytically this evidence lower bound. And then you can again use things like stochastic gradient descent in order for you to try to maximize the lower bound, which then gives you some reliable estimates of a parameter. So the loss function here, the idea of loss functions that tend to show up when you learn using deep neural nets, is this evidence lower bound. Okay, so that's the basic idea behind DKF. So where's the reinforcement learning here? So that's where our additions start to come in. So the idea for reinforcement learning looks as follows. Well, originally we just had the Zs, our latent states, which is how things are evolving in the world, but we don't observe them. We have the observed, which is the X's. Our actions must affect the latent state, and it must affect what we observe as well. And the actions that we take should somehow depend on what we observe. So we modify the graphical model to incorporate this. And when you include this, the effect of the actions, you change the conditional independence and the conditional distributional structure of the generative model to incorporate actions in the mean and in the variance of all of both the latent states as well as the observed. Okay. That's one thing. You also need, if we're doing any kind of reinforcement learning, you need a reward. So you also have to have the reward being generated by, again, what is the true latent state? And in principle, you could also have an arrow coming in from the x's as well, okay, into the rewards. And the rewards are also dependent on the actions. And again, we make some general framework for that. And again, neural nets everywhere, right? Deep neural nets everywhere for all of those functions. So once again, in order for us to learn, what we're going to do is we're going to take the idea of batch reinforcement learning here. So we're going to freeze the network for the actions. You're going to learn the network for the latent and observed. Then you're going to freeze the network for the latent and observed, learn the network for the actions, and vice versa, and fluctuate back and forth until you've minimized loss. Okay, until you've minimized the evidence lower bound and, maximized your expected reward, right? Because those are two separate stages. But in order to do it, you once again do need to have a variational approximation because the posterior of Z is once again intractable. So there's another layer on top of this in order for us to do it. So I'm not going to go through the specifics of the network. I will just say that I lied a little bit in this diagram by saying that the actions depend on X. They don't. They actually depend on another latent variable, which we use a GRU, a gated recurrent unit, to keep in a data efficient manner the whole history of what has happened in the real world. So the state, reward, and actions go into a GRU, and they emit hidden states from one layer or from one timestamp to the next. And our optimal actions are based on these H's, on the hidden layers that come out of this GRU. Okay, so what are some, I already mentioned how the batch reinforcement learning works. As I said, you do it in 2 stages. You freeze action parameters, optimize over the neural nets that tell you about the generative model, then freeze the generative model, optimize the actions by maximizing the expected reward, and iterate over and over. So we've done this on a few different stocks, Intel, Vodafone, Facebook, Microsoft, and we've also done the simultaneous, the analogous analysis using 7 other models. So TWAP, Q-learning, DynaQ with an AR1 model underlying it, DynaQ with an LSTM underlying, DynaQ with a Deep Kalman filter underlying it, reinforced Deep Kalman filters where we don't include variance as one of the network that we're optimizing over, and then the reinforced Deep Kalman filter when we do include the variance. And the way that you read this panel, it's a little bit confusing, but once I explain it, it'll make it clear. The first row is take the label at every column, subtract what TWAP would do. This is the relative performance. So in other words, the first top left histogram is a relative performance of Q-learning to TWAP in basis points. On the first row, the second histogram is a relative performance of DynaQ AR1 relative to TWAP, etc. The second row is the relative performance of, say, DynaQ AR to Q-learning. And then that one, maybe I should use a pointer so everyone can see. That one is the relative performance of DynaQ LSTM to Q-learning, DynaQ DKF to Q-learning, etc. So if you focus on the last column, this is RDKF relative to everything else. And if you look at it, you can see that the mean, the lower and upper quantiles are all above 0. They're significantly, in fact, above 0. If you make 0.5 basis points, 1 basis points, 2 basis points, that's a lot already. So this is outperforming a lot of these strategies in a very, very convincing way. And this is consistent across a sequence of different assets. Now, I'm not going to lie to you. This is not easy to do, okay? You can't just, open up your Jupyter notebooks and code this up in an afternoon. Okay? It takes a lot of sweat and tears to get this working very well. But the underlying framework is very flexible. And it doesn't have to be applied particularly in the algorithmic trading context. You can apply it in pretty much any other area that you would like to use some sort of reinforcement learning methodology in that incorporates all of this sort of evolution, sort of time dependence in your data. Yeah?
My question is, so the unobservable, the hidden, the latent variable in your Kalman filter is,
let's go here.
Is the Q value actually, the weights of the network
There's
that
no,
will
in this
approximate the...
In this part of the talk, in the reinforced Deep Kalman filter, notice I never said Q function anywhere. There's no Q function here. There's no Q value coming in. What you're doing is, in the batch reinforcement learning context, what you're doing is you're freezing your actions, your action parameters, which tell you how to behave given all of the other information that you see, which is also being inferred, right? Zs are being inferred in some way.
Right.
Then you're optimizing the actions, not by trying to find a fixed point equation for the Q function, but rather by explicitly maximizing the expected discounted rewards.
Right.
So it's an explicit maximization of that expected discounted future rewards.
Okay.
So the Q function is gone from this
Okay,
part.
I see.
Yeah.
I see. I see. So another question is, so since now you're using Kalman filter, so it will not only give you the first moment, I mean the approximate mean of the discounted reward, but also the second moment, you know,
Sure.
the variance, and you can use that for risk. I mean, it's not so
Yeah.
you just don't not just maximize discounted reward, but also you can minimize risk. So you have a multi-objective like.
Oh, certainly. So you can modify your reward function not just to be discounted rewards. You could incorporate a risk term in there. In fact, in the analytical work that I talked about in the beginning, remember I mentioned that there was this reward which is from trading and terminal value of your assets, and then we had this extra term which I said I'll reinterpret it for you as model uncertainty. That's a risk-like term. When you're doing this, when we were discussing the Q-learning, we didn't have that extra risk-like term. It's easy to add it in. And in particular, as you mentioned, yes, your posterior distribution, your variational approximation, as well as a generative model, has a variance in it, right? There is a parameter sigma. You can certainly use that as part of the penalization in the reward portion of the reinforced batch, of the batch reinforcement learning procedure. Yeah. Yes.
So I found it a bit confusing, this Kalman filtering aspect. I guess you are algorithmically not using the Kalman filter, right? You are doing variational inference.
You're doing variational inference, yes.
Okay.
Yes. Yeah, I mean, so Kalman, that's why I started this off by saying, okay, I need to say what is Kalman filtering, first of all. The fact that you're trying to infer filter Z from the observed states, right? That's what Kalman filtering is when Zs are driven by an AR1 Gaussian and Xs are in a fine transformation. You can do this inference very easily, and you can filter and you can smooth. The problem is when you generalize it to have these neural nets sitting in the means and the variances, that posterior is no longer analytically tractable. And that's where you do the variational approximation, which is getting the parameters from the variational approximation of the evidence lower bound is what you would call variational inference. Yes. It's related to also variational autoencoders for those who know anything about that. Yeah.
Okay. In this report about the Q-learning and the deep Q or DynaQ is Q-learning is to optimize the Q function, and the DynaQ and deep Q is try to optimize the loss function. Yeah, is it right?
Yeah. So Q learning and DynaQ learning uses this iterative algorithm to try to solve this fixed point equation.
Of fixed
right?
point.
Yeah. You're trying to solve for the Bellman equation.
Okay.
And DynaQ and Q learning do this. And
Deep Q.
when I talk about the deep Q learning is also attempting to do it by replacing solving this fixed point equation by minimizing this loss, where you take a sum over the replay buffer. Okay, so you have there are a few layers here, but you have the sum over the replay buffer, and then you minimize that loss. The goal is, the hope is, where there's no proof. Okay, this is the problem. There's no proof, but the hope is that minimizing this loss does give you a fixed point solution to this
same
fixed point
solution
equation.
for solve the fixed point equation.
That's the idea. The idea is that this loss function is motivated by this fixed point equation. Because if you look at this loss function, what is it? It's simply the difference between the left and right-hand sides, where you replace the expectation, difference between this and this, right, squared, where you replace the expectation by a one-sample Monte Carlo estimate. Yeah.
Sorry, about the same point. So, I mean, even for simple Q-learning, let alone when you add deep networks into it, one assumption for reaching the convergence is stationarity of the reward function. But in the in markets, in stock markets, so I don't, does the assumption hold? So it
depends by what state variables you input. If I try to look for stationarity by just putting price as a state, probably not. But if I put in a sequence of prices, maybe. If I put in a sequence of prices and a sequence of the quadratic variations, now perhaps even more likely. If I include also cancellations and additions of the limit order book, now maybe even more likely. So the stationarity, I think, it's too broad of a brush to ask the question, is it stationary? The question is is it stationary when you look at what set of variables? Right. Markets could be stationary when you look at the correct set of variables. It may not, I mean, I don't believe that they are completely stationary nonetheless, but I think if you include enough state variables, you would have enough stationarity over a reasonable amount of time. Right? You're not going to do it over decades, but over, week, month. If you incorporate enough of the observations of high volatility, low volatility, combined with high cancellations, low cancellations, combined with large volume, a lot of liquidity, low liquidity. So you need to have an experience of the world, enough experience of the world for you to do this. And given that data is at very high frequency, I think that in certainly liquid markets, you're going to be able to get a reasonably good model for reasonably short amounts of time. Yeah, there's a question back up here.
Thanks. Sorry if this is a basic question. I'm not very familiar with deep and reinforced deep Kalman filters, but I've used Kalman filters in the past.
Yep.
So from my experience, I saw the hint earlier on in your talk when you're talking about states and actions and things like that you were going to allude eventually towards a Kalman filter, I was guessing. Typically, you have a model where you can somehow predict the next state, and then you might take some kind of derivative of or whatever to calculate that and then do a difference and work out from there. In your deep Kalman filter, is that captured in that neural net? That is the state model somehow discovered?
Yes, it is, because when you write that, so the difference between, again, the difference between the Kalman filtering setup of the problem and the deep Kalman filter setup of the problem is just what are the means and the variances. There's still conditional normality going on here, but the means and the variances are now some nonlinear functions. So you do have one step ahead predictive power. You do not observe z's, so you still will have to infer them, and that's where the variational approximation comes in. And when you maximize this evidence lower bound, you're both maximizing the approximate distribution as well as the generative model. So once you've maximized that and you believe you have a good fit, you can now go back to your generative model together with your variational approximation, which will infer what z's are, and then use a generative model to try to predict where they would be. Yeah. So those parameters are obtained here, just like in Kalman filtering. Yeah. Just a more complicated version. Yeah. Okay, so I think that brings us to the end, effectively, of the reinforcement learning part of things. And I will do given that it's 10 after, maybe a 5-minute version of the mean field game formulation of all this. But now it gets into more, how should I say, just a fun mathematical world for those who are interested. So let's go back to the original formulation in the mathematical framework of the problem. So there, you might recall what we had was maximizing the expected terminal value of cash from the agent, subject to a terminal penalty on inventory, together with some sort of risk-like term. And what this slide is telling us is that you can actually reinterpret that risk-like term as the agent protecting themselves from model uncertainty. So you may have a model in mind for the world, but there's all these other models that are out there that are possible models. You're going to pretend or try to optimize your trading strategy as if the universe is going to throw one of these other models at you, even though you believe in this one. But if the universe throws you a really ridiculous model, you're going to discount it. So if you believe, for example, that the rate of up and down movements is 1 per second based on historical data, but the alternate model is that it arrives 1,000 times per second you have an up and down movement. That's obviously a ridiculous model. You shouldn't account for it equally as an alternate model where the up and down movements are, say, 1 every 2 seconds or 1 every half second. Right? Those are maybe a little bit more realistic. So there's a notion of the distance between those alternate models and yours. And the distance, if you use this something that is effectively the Kullback-Leibler divergence or relative entropy between your reference model and a candidate model as a penalty, that turns into effectively a quadratic variation type risk term or something that is related to variance of the P&L. Okay, so it's connected somewhat to your question before. One of the interesting outcomes of that is that if you look at what the optimal action of the agents are, of the agent, this is a single agent problem still, is it turns out that the agent behaves as if the model has the drift that they had originally assumed, but there's an extra negative drift whenever they have long inventory and an extra positive drift whenever they have short inventory. In other words, they're trying to protect themselves from being wrong. Because if I have a long inventory, what's bad for me is that prices go down. If I have short inventory, what's bad for me is that prices go up. Okay. So that's the outcome of some of the mathematical analysis based on the work that I've done with a former student of mine, Ryan Donnelly, and Alvaro Cartea. Ryan's at King's, actually. So now what I want to talk about is an n-agent version of this, and I'll give you the mean field game solution. So imagine now that the single agent problem is what we've been talking about. But really in markets, you have many agents. You have all of you that are trading and trying to optimize. And you're all a little bit different. There might be a group over here that is on average long, and a group over here that's on average 0, and they're just stat arbs, and a group over there that's on average short. And maybe the people that are doing stat arb are co-located and they have very, very low impact on prices when they trade. But the long and short holders are institutional investors, and so when they trade, they have perhaps larger impact on trade, on the market. So there are different types of agents out there. As well, you may have different models. Stat arb people might believe that prices are mean reverting because that's how they're trying to make money. And the long and short holders might believe that the asset is going to go up and the asset's going to go down. And they're trading all at the same time. How do we optimize and how do we find an equilibrium in such a market, in this sort of multi-agent game setting? So one way to do it is simply to just make some ad hoc assumptions on how the traders are going to behave, then run in the system and see what happens. We don't want to do that. We want to generalize the idea here to the multi-agent setting. So what we'll have is, in fact, I don't have all of the equations written down because it would just become horrendous. What you do is you take each agent solving a control problem, much like this one, where the action of all agents affect prices. And agents are only subject to the information that they have access to. So I can only trade based on information of my own inventory, of the total order flow in the market, because you can see that, but I can't see a particular individual agent's order flow, as well as what prices are doing. So this is a filtration that you have information that you can trade on. There may be other latent variables that are affecting the markets that you cannot see. So what we want to do is find a Nash equilibrium. What you want to do is you want to find the trading strategy which, if I deviate from it, then I will be worse off. And if everyone is following a trading strategy for which if they deviate, then they will be if they unilaterally deviate, they will be worse off. This is called the Nash equilibrium. We cannot solve this in the finite player game. The problem is the information asymmetry. I don't know what everyone else's inventories are, so I cannot solve this finite player game. But if you take what's called a mean field game limit, where the number of agents go to infinity, so the ratio of the groups, the groups stay in the same size, the relative size of the various groups stay the same, but you take the number off to infinity, then you get a version of this stochastic game which you can indeed solve for a Nash equilibrium. And then what you can do is take that solution of that Nash equilibrium for the infinite player game and tell the finite player game agents how they should trade using the solution that you get for this infinite player game. And what you'll find is that when the finite players trade using that strategy, they indeed are close to a Nash equilibrium. They're close, and how close are they? They're close effectively on the scale of 1 over n, where n is the number of players. So you can actually prove these things. And I think for this audience, I'm not going to get into the technical details of this. That's the main theorem that comes out of it with my former PhD student. So there's a whole bunch of fun things in convex analysis that show up, forward, backward stochastic differential equations, solving those, and then you get very generic solutions. What you can understand is this, I think. This would be an easy way to explain. What we have here is a simulation based on a model that was estimated on data. So we took real data, wrote down some sort of hidden Markov model for how the world is evolving, estimated those parameters for a data set. I can't recall which asset it is, and then we simulated an environment which follows that, which follows the same parameters as the parameters we estimated, and pretended that we had two different types of agents. We have the red type agents and the blue type agents. The red type agents are stat arbors. The blue type agents are liquidators. So blues are on average positive inventory. Reds are on average at the start, are on average short, or sorry, zero. And they also had different beliefs. The model that we used is a model in which the price mean reverts to one of two levels, and it may switch. So it may be, first of all, prices are getting attracted to a certain level, and then it switches. And it switches at a random time. You don't know when. That's hidden to the agents. The long holders are assuming at the start the prior distribution on which of these two things is true is 90%, 90% to the positive state, to the increase in price, and the stat arbs believe it's actually the other way, 90% to the lower value. And that is illustrated in that posterior, so that's the prior, right at the start. The posteriors, as they observe data, they start to converge on their beliefs. Okay? They eventually converge on what they believe the actual evolution of prices are. And what's shown in this panel here, the left panel, is the inventories of those agents. So you can see in blue, they on average sort of decrease and then eventually get down to zero. And the red agents, on the other hand, are going both positive and negative, and positive and negative, and they eventually converge down to zero. So they're taking advantage of statistical arbitrage opportunities in the market and knowing that these liquidators are there. And the liquidators are also trading in a way that protects themselves from the fact that they know there are the stat arb people that are trading in the market. Although each individual agent doesn't know what each other individual agent is doing, they know in aggregate what they will be doing, and they react accordingly. So it's possible to actually solve these types of problems, and you can extend this into many different classes because the theory works for an arbitrary number of classes. Implementing it numerically is where the challenge is, but we're hoping to extend this into many other areas, and I think I'm going to stop there by just putting up this quick slide. So one thing we want to do is look at more assets, add additional features to RDKF, use model-based acceleration because we haven't really utilized the fact that from the analytical work that we have very beautiful closed-form formulas that apply within this linear impact model. So why not use that as sort of a starting point for a deep learning type and reinforcement learning type algorithm, rather than just starting the reinforcement learning at some, in the randomized network setting, which is what people often do, as well as the effect in spoofing and optimal discretion, and a lot of other things that we're doing together with Alvaro and a bunch of my other colleagues. So with that, I'll say thanks a lot for your attention, and can keep taking questions.
Thank you, Sebastian. So